So hello, everyone. I am Nathan Rawling. I'm a facilitator here in the electronics, 3D printing, and metal shop. I joined MakeHaven about a year and a half ago. I have been using electronics and computers like pretty much my whole life. I started out like soldering when I was a kid, lots of nice little burns and things. But then I went to school for a while for computer engineering, ended up working in tech for a really long time. I still work in computer software, but not so much hardware. But I'm happy to introduce you all to the wonderful world of electronics. We also have a very active radio bench downstairs. So a lot of the recent work that I've been doing in electronics has actually been around the radio bench. So for this week, we want to cover just some very basic introductory, concepts around electric circuits and electronics. And the different sources of power that we have and sort of the different levels of permanence that we have in electronic circuits. And then after class, we'll do some soldering. Just going to minimize my little Zoom overlay here. Circuits can be, there's like lots of different sort of layers to understand, but at the most basic level, what you have is electricity, and it's flowing through what essentially you'll see in these slides, we use like a plumbing model to describe them. But this triangle that we have of the relationship between power and voltage and current is really sort of the fundamental way that electrons pass through substances. So whether it's wires or salt water or any of those things. But the relationship between voltage and current and power is basically what makes all of electronics possible. So whenever we're making a device that's an electrical device, we're manipulating these relationships to accomplish some goal. Oops. So voltage is really the amount of energy and voltage that's available in the circuit at the point where you're measuring it. Higher voltages are more dangerous than lower voltages. Both voltage and current can be dangerous, but the voltages that we're working at in DC circuits are not dangerous. So just like handling like a 9-volt battery out of a drawer, if you touch it to your tongue, that's one thing, but like a little stimulating, good way to detect if the battery is charged or not, but it's not going to hurt you. Whereas, when you plug something into the wall, that voltage is 120 volts here in the United States. And that's a little bit more dangerous voltage. The reason why the higher voltages are dangerous is because they can travel further through your body and then interact with your body systems. And that's really what makes electricity dangerous. Also burns. So high level takeaway is nothing that we're working with our soldering projects is at a high voltage. We do have some soldering projects at MakeHaven. The new door control boxes, which are featured on one of the slides, do have a high voltage side and a lower voltage side. And you'll see it's indicated very clearly on the board which side is which for this reason. Because
card readers?
Yes.
Oh, nice.
Yeah. So one of the other parts of the relationship is power. And power is telling us sort of how much total energy is getting used. One of the things that's kind of tricky in how we organize the slides is that power is actually voltage plus current together. So voltage times current gives you power. Power is measured in watts. And then watts over time gives you watt hours. And that's what we pay to the electric company. So like when you read your meter and it's labeled in kilowatt hours, that's a kilowatt for an hour. So if you run your dryer, which is probably around a kilowatt, electric dryer for an hour, then you're going to pay for 1 kilowatt. So if you have a device that's pulling twice as much power as your dryer, then you can run it at half the time and use the same amount of overall power. If you have a DC device like a LED bulb, right? Because we've been replacing all of the incandescent light bulbs from my youth with fluorescent and LED light bulbs. The reason why they're so much cheaper to run is because the voltage is so much lower and the current is so much lower in those. So the overall power equation is just much simpler. The bigger the power drain, sort of the more infrastructure you need to support it. Did I skip current? It did. This is how we got into trouble. So current is the measurement of how much of the electricity is flowing through a particular pathway, right? So if you think of voltage as being kind of like the pressure of the force, right, of the measure, current is like how much, right? So current is measured in amps. And if you have ever looked at your fuse box for your circuit breakers downstairs, they're all, or in your car, they're all measured with a certain number of amps. So those are designed so that when they hit a certain amount of current flow, that they will shut off. And those current flows are once again sort of tailored around the devices that are connected, but also the safety hazard that they create. So anything over 15 to 20 amps starts to be where it can cause death or serious injury to a person. So a 2 amp circuit breaker, right? If you like, even a household current is not very dangerous. 20 amps is more dangerous. A 60 amp breaker for like your stove or whatever, that's why everyone gets nervous around this thing. But this concept, right, that voltage is how sort of much pressure is being pushed on the electrons, and current is how many of them can flow through, is sort of the important distinction between these two things. Any questions so far on that? All right. So to make an electronic circuit, you have to have a closed path. Right? There has to be a way for the electrons to get from one end of the circuit all the way to the other. So that's called a closed circuit because there is at least one loop where the electrons can make the whole way through. If you have an open circuit where there's no pathway, then the electrons cannot flow. And so your circuit's not going to work. This is actually how switches work. So when we turn off the light switch, then the electrical pathway between the main power and the light bulbs is now broken. So the electricity cannot flow through and the lights do not come on. Then we have short circuits. So short circuits are where we have a closed circuit, but maybe a path of that circuit that's closed that we don't expect to be closed. And the two important like examples that are on this slide is you can have a short circuit where part of the circuit has been sort of cut off from the flow of electricity because it's easier for the electricity to flow through this other pathway. Electricity will flow through all of the paths, but relative to the amount of resistance in that path. So because it's a lot easier for the electricity in this example, that's the second one from the right and the bottom, it's easier for it to just flow through the wire than to flow through the light bulb. Almost all of the current is going through the empty wire. The light bulb probably wouldn't shine at all. In the lower right-hand corner, we have a short circuit that's short-circuiting the battery entirely. So what will happen is that battery will heat up because so much current is flowing. The wires will heat up and the battery will very possibly catch fire. This is actually why lithium batteries are banned on airplanes. Batteries can actually do this internally. And that's actually, another issue with the lithium batteries is they if you have, the battery is like a metal tube that has chemicals inside. And if the metal tube shorts, there's like a little insulator at one end. And if it shorts from the outside of the tube to essentially where the little pokey part is, where the positive connection is, then you don't even need wires. And it just, so most alkaline batteries that we buy, Duracell, Energizer, it's not a big deal. They'll heat up, but it's, they don't have that much power in them. But lithium batteries can discharge virtually all of their power very quickly. And so this type of short circuit is a big problem. And when you look at like integrated circuits that have like many paths, like I have no idea how many distinct pathways are in this circuit. But what I do know is that if you get a short like this, which you can create pretty easily accidentally, it will start to heat up. And so my wife was actually working on an Arduino based circuit, and she had a short in the part that she had soldered, and you could feel like you could burn yourself on the chips in the circuit. So definitely short circuits are a big problem. So now we're going to talk a little bit about power sources. Most circuits have just one power source. It's mostly just because it's easier. There's no actually strict reason why you can only have one. So frequently for small electronic circuits, we use batteries, AA batteries, AAA batteries, 9-volt batteries, or you can use USB connections, whether they're plugged into like a wall wart transformer or plugged into like a computer. The only sort of warning that I would give about using USB to power your electronics is it is possible to damage or destroy USB ports on laptops if you connect bad circuits to them. So USB is a great way to get power, but when you're first prototyping a thing, I suggest not actually powering it from the computer if you can help it. My son's laptop is constantly screaming about overcurrent on its USB ports because he's created short circuits on his Arduinos. The other most common source of power is using wall power. So plugging in like a big DC power supply, or using 120 volts, or using some sort of lithium batteries, or there are other batteries that can have this problem too, but lithium ones are the ones you see most often, where like if you have a short, a big desktop power supply like that one can provide 30, 60, 100 amps of power. So if you short that, it's going to heat up very, very quickly. Not necessarily the power supply, because it has protections built in, but the part that you're working on. So there's the way to think about it generally is that the power supply is really supplying all of the energy needed for the circuit to operate. And the circuit can modify that supply as needed. So for example, in the Arduino kind of infrastructure, the components generally use 5 volts or 3.3 volts. Well, Arduinos have a built-in voltage converter that will step down from 5 volts to 3.3 volts, so you can connect any peripheral to it. But the power supply that you connect to the system is a 5-volt system. Similarly, like a computer, a big desktop computer at home will plug into the wall, gets 120 volts, but the various components in the computer might run on 12 or 5 volts, depending on what they need. But once that voltage is determined, all of the components that are connected to that circuit have to work at that same voltage. If the voltage is too low that you're supplied, then it's probably not going to work. LEDs that don't have enough power won't light up. If the voltage is too high, it may work, but it may start to heat up because all of that extra energy has to go somewhere. It's going to get dissipated usually as heat. If that heat starts to build up, then it can, it's either going to burn out the parts, which is very common with LEDs and transistors, or it can catch fire. Usually they'll just burn out before they catch fire, but every once in a while a part will catch fire. And then all of the various components together determine how much current is needed. So when the circuit is operating properly, the voltage is getting converted into a certain amount of heat by the natural and proper operation of the components. That heat is really coming, that's the current that's consumed by the circuit. But you can measure that at the power supply as well. But the power source has to be able to supply that much current. If it can't, the circuit will just kind of not work. It might work some and then fail, it might work intermittently, or it might just not work at all. So if the current demand is greater than the supply, the circuit won't work. Do we need to admit NN?
Yeah.
But if the supply, if the power supply is capable of providing more current than what you need, that's not a problem, right? So if the power supply voltage needs to match whatever it is that's consuming it, right? So if I have a 5-volt power supply and my components expect 5 volts, that's fine. If I have a 12-volt power supply and my components expect 5 volts, no go. Basically the voltage has to match more or less exactly. There's a little bit of window, but pretty much. Current, the power supply has to be able to supply as much or more current than the circuit is going to consume. Does that distinction make sense? And then how permanent does your circuit need to be? So this is where we talk a little bit about all the different sort of ways that we can build circuits. So a lot of circuit design, we're going to start with some sort of diagram that tells us how the components relate to each other. And every type of component, resistor, a diode, a battery, has its own symbol, standard symbols, ISO symbols. And how we combine those things together shows how the circuit works. This type of diagramming has been around for a long time. It's been used for, I think, about 100 years. And people who are skilled in reading these diagrams can reproduce any electronic circuit from the diagram. Because all the information that you need to build the circuit is really in the diagram. The sort of next level up, right? Once you're starting from a diagram and you need to prototype what you're going to build, you need to make sure that the circuit actually works. You might use what's called a breadboard. And nowadays we make them out of plastic. They're plastic and they have like spring metal catches in the bottom that grab on to the pins and the components that you shove in. And they are connected in rows across the breadboard. So you can stick the connections in, make temporary connections, and then add additional connections in between rows using wires. But the parts can fall out, the springs get worn out, and your graduate TA can come through and just pull all your wires out when you're trying to debug your circuit, because usually the problems are in the wires. So my graduate TA would come and just pull all the wires and make you do them again. So, little bit of trivia. They're called a breadboard because they were originally made out of bread. They would take a piece of white bread, shove the components in it, and it would hold the components in place while they did their circuit. This is a lot nicer, it doesn't spoil. We have several breadboards downstairs. I have no idea what shape they're in because I haven't used them. But they are cheap and easy and a really great way to get started building something, especially if you're trying to build from a diagram, whether it's a sort of classic diagram or even one of the sort of newer diagrams. Perf board is like the next step up from breadboard, and you can actually get perf board that is milled so that the holes are the same as the breadboard. So that's called actually like the pitch of the holes. They have all different sort of spacing on the holes. So you can get ones that have holes that are really close together, ones that have holes that are really far apart. But it's not a bad idea to order the ones that have the same size as the breadboard, because then you can take your design from your breadboard, which was working, and then just copy it right over onto a perf board. And they work great for through-hole parts, which is what's pictured on there. The parts, basically the pins from the parts go all the way through the board and then are soldered on the other side. And that holds them in place and creates the electrical connections as well. Usually, once you solder these in, you usually leave them. Like these are build once, and, forget about it. You can like adjust these circuits a little bit, but the more you solder on the parts, the sort of more janky they get. But that's pretty much like the getting close to the end of what you can kind of do as a hobbyist by yourself. You can create milled PCBs by taking a solid copper, copper plated board, drilling your own holes, and then milling out the copper or etching out the copper traces. That's what these milled PCBs are. There is software for doing this. I think they did it for the toolbox project downstairs. I've never really done it. I mostly just do perf board. And I don't know, like the amount of effort that you have to do the milled PCBs is not that much less than doing design where you order them. The only downside of ordering PCBs is usually there's a volume restriction. So you might have to order 100 boards because it's far more cost efficient for them to do the tooling for the machinery to do a large number of them. But so like the MakeHaven boards that are used for the bicycle class were all just, we designed them. I think Iris designed them and then just ordered them. And so they came pre-made and we just add the components. So that's the end of the slides for tonight. And next up is the soldering. Any questions?
The bicycle class, what are you guys doing with the board?
Well, so yeah, so here's instructor's show and tell. So I took both of Iris's really excellent soldering classes, and you make these little things that are designed to go on bicycle spokes. So you zip tie them to your bicycle on the wheel, and then as the wheel turns, there's a motion sensor. So like a ball switch, so that as the wheel turns, the lights come on or off. It actually has 3 colors.
Oh, that's cool.
But usually we just wire it so that just one of the colors is controlled by the ball switch.
Like a night light for a spoke almost?
Sort of like if you wouldn't be able to see it very well during the day. The LEDs are pretty bright, but they're not super bright. Mm-hmm. But like if you're like at twilight or whatever you're driving around, you'll see every turn of the wheel, you'll see the green come on and off. But I brought these today because there's like, I talked a little bit about through hole parts for the perf board. There's a version of the class where you do the through hole soldering, which is the beginner soldering. That's what we're going to do today, where the components go through the board and you solder on the back. And then there's also surface mount soldering, which is sort of the more modern, smaller components where the components are actually mounted on the surface of the board. And what I really wanted to show, and I'll show on the camera as well, is how much smaller the surface mount one is. You can see that in both of these designs, like the battery is taking up most of the space, but there's a lot more space taken up by components on the through hole version than on the surface mount version. And the surface mount version has like tons of unused space, right? Like this could actually have been made smaller. But so these are fun. Even though you're going to learn soldering today, Iris's class is really great.
Question for you on the surface mount.
Sure.
So I was told that like there's like with soldering, obviously you're going at it with the soldering tip, but with the surface mount, is it some sort of glue? Oh, thank you.
So there's several different approaches for surface mount soldering. One is using a soldering iron. So that one was actually done using a soldering iron.
Oh, okay.
Then there are versions where you use a solder paste and you cook it in an oven, right, called a reflow oven. Yeah. We have one downstairs. I cannot recommend using it. Well, Iris told me it was bad, and then I tried it, and yeah, it's bad. So it's very tricky. Like reflow ovens are really great for doing really repeatable soldering, right? So like if you needed to do 100 of them, you would want to use the reflow oven rather than doing it by hand. But getting that sort of like dialed in for whatever it is that you're going to make, you're going to wreck 5 of them, first. So I didn't have 5 to rack. I racked 1, called it good, and then made the other one by hand.
That's awesome.
Whereas, with the hand soldering, it takes longer. It takes a lot of attention, but there's almost nothing that you can do that isn't fixable, which is one of the things I like about soldering. I make a lot of mistakes. When you're like milling on the vertical milling machine downstairs and you cut too far, parts wrecked, toss it, start over, right? Wood, same thing. Oh, I cut it too small, right? That's why we measure twice and cut once. No, I cut it too small, not stretch.
No, it's firewood. Perfect woodwork.
Well, maybe it's softwoods, so but like now I have to repurpose it out of my project. With the hand soldering, the nice thing about it is there's almost nothing you can do wrong that's going to make the whole thing jump. You might wreck a component. When my wife took this class, she broke 3 of the ball switches because it turns out they're the weakest part of this whole circuit, followed by the battery adapters, which are the second easiest part to break. But I find it's very soothing. I enjoy it. It's calming. It's kind of like a meditation almost. Any other questions? All right. You want to say goodbye to the remote?
Do some soldering. Yeah, unfortunately, we are. So as I said on the Slack last week, I think we're going to be shifting more into doing things in class is a bigger part of the class. So trying to try to come in person if possible. I'm just speaking to the people online. Because this week, next week, I think 1 or 2 more weeks.
Yeah,
that,
so there's basically in-class projects for I think each one of the electronics users, but like the plan was that half the class would do soldering this week and then half the class would do soldering next week. So if you can come in next week and learn how to solder, that would be great. And then the other projects you don't necessarily have to do here. I think there's like a pick your project and then work on it and then bring it back. But if you need help with it, you can either come to class with it, or I have hours on Sunday mornings, and you're welcome to come in on Sunday mornings. And that can be done.
I have my office hours Sunday at noon as usual. So that would also be a time to work on things. But we will say goodbye and sign off.
Bye, classmates.
The internet.